All right, so hope you have started a good semester so far. Enjoyed your weekend, the first weekend before the storm, and then so I managed to upload the primary resources on your wiki page. So just go to the course website, and it's going to direct you to this wiki page. So our section is EECS2021E, and so within 20 hours of each of the lectures, I'll try to post new lectures here. They're mostly from the publishers, slides with minor tweaks, perhaps, or if something changes while I'm presenting, I might update them later as well. But mostly they're similar. We're trying to conform with the reference book as well. So this is the high-level agenda of the labs. Your first lab would be next week, Monday. So check your registrations. You might be registered in either of the labs, either lab A, 01, or 002, or B. We have limited seats there, so make sure you attend your own specific labs. Because when you submit your grades, you need to submit to that specific pool. Spend some time to read the rules at home. I'm just going to showcase you the website. So gradually, by each week, I'll try to make these assignments available. So the first 4, as I mentioned before, are before your midterm. There is one makeup before the midterm for the 1 to 4. So if you miss with an emergency or anything else, that might happen sometimes for us. For the first 4, you have an option to have a makeup lab. And then if you missed one from 5th to 8th after the midterm, you have another option for another makeup. So the first 4 labs, we will use that RVS simulator. So these are the links and the manual. Make sure you spend some time this week before your first pre-lab, which is next week, Monday, to learn about the overall view and the manual. And after midterm, we're going to use the Verilog simulator, which is this Icarus. So it's a compiler for Verilog. So the first 4 are the assembly using the simulator, and then the second 4 are the Verilog one. We were just assigning your TAs today, so by tomorrow or maximum on Wednesday, I'll post another notification regarding your TAs. So each of the labs, you have 2 TAs available. So for lab A, you have 2 TAs. For lab B, you have another 2 TAs at the lab session. So the first few weeks, I'll be physically there as well in case something was going wrong or we needed to change some permission, or because we are dealing with 70-something computers and a submission system. Do you need a chair? Yeah, take this if you want. There's also 2 over there. So about the labs. So you have 90 minutes pre-lab. So a few days before your first lab, or each of those labs, I'm going to post your pre-labs. So it's a set of instructions. It's a PDF with a set of instructions that walk you through what you're expected to do in the lab test mode. So in the middle of the lab, which is almost 3 hours, you're going to have a break, and the computers are going to get into test lab mode. In the test lab mode, you don't have access to internet or communications with others. Cell phones is strictly prohibited. So please make sure you read and learn about the rules, because TAs are instructed to give you 0 points if they see you using your cell phone. Just treat your lab test mode as your actual exams, so lab exams. So the first half of the lab, you're going to walk through with that pre-lab PDF that I'll post before the lab. So you're going to start using the RVS simulator. And so let me just show you if I have it here open. So this is the simulator. So these are some assembly instructions that you're going to learn, start to learn as of Wednesday. So when you write some assembly in RISC-V, it's going to compile, and this is your hex, and you can actually run it and see the memory dump, and it's like an actual simulator for RISC-V. So say in your instructions you were given to write and add I codes, right? You can just write it down here on the first pre-lab and then compile it and see the output. And then when we came back from the break in the middle of the lab session, so after 90 minutes, the second 90 minutes, which is sort of 80 minutes, the second part of the lab, your computers will turn into the test lab mode. So you're going to cut access from the outside board, and you're expected to follow through the rest of that PDF, which are the actual questions. And then at the end of the lab, you submit a file, a text file, of the output of this. You just go to the files, do the save as, save it as a file, and submit it. In the lab, I'll give you the instructions. They're also available on the website. So just spend 5 minutes, you're going to learn everything. There are 2 TAs available there. I myself would be there as well. So hopefully we don't run into any issues. Questions?
Are we allowed to make notes on the pre-lab and then use it during the actual lab?
I don't think so. I mean, I don't mind, but the point is there are 3 sections in this course and around 400 students. We want to make sure the fairness is for everyone. Otherwise, if you have a notes or if you don't, it doesn't change my life, you know. Since we decided that you cut access from the outside, and you got the instructions in the pre-lab a few days before perhaps, and inside the pre-lab, so you should be able to start, you know, testing yourself in a test lab mode. So 99% no. If something happened, I'll let you know in the lab session.
But if everyone's able to take notes, then wouldn't that be considered fair?
You know, it's just not it's not a matter of taking notes or having a calculator or having a scientific calculator or having a calculator on your cell phone. It's just some ground rules that we've set, and then we follow through on that. Yeah.
Will we be using Moodle to post course updates?
I don't think so. I mean, if it's really needed, I can set up Moodle, but I think on Wiki I can set another tab and then I just send you by email or make you available at a certain way you can access it yourself. I mean, but if Moodle has a specific functionality that you definitely need to use it, let me know, email me, and I'll consider it.
Yeah, so in regards to that, right, because a lot of us use Moodle to kind of see our grades and be able to gauge where we're at. So without Moodle, how would you be able to do that?
Do what?
To like see our grades. Like,
I mean, no worries. You'll find out about your grades. Yeah, that's the last thing you have to worry about. No worries. So, yeah.
So there are no labs. There are no labs this week.
No, not this week. But starting from next week, you're gonna have your first lab. So a couple of days before, I'll update the pre-lab for you guys. You can also download this and access it from your own computer at home, or even connect to the lab machines. There are several ways you can start working on and using the manual on that. Yep.
How do we connect to the lab machine?
You're actually physically there.
Oh.
Yeah.
How do we can do it?
No, I mean in the test lab mode and also in the pre-labs, you need to be physically there.
Okay.
Yeah. Okay, all good? Cool. All right, so we started last week. Yeah.
Sorry, just one more question about the labs. The labs, the marks are just going to be based on a test, right? Nothing on the pre-labs?
Actually, yes and no. Because if something goes wrong, if your file is corrupted, if, I don't know, an earthquake happens and the electricity runs out and whatever, we can have a sort of a follow-through of your pre-labs and see how you were progressing. So that's a good trademark for us to see your progress. So that's why you need to submit the pre-labs as well. So that's mandatory.
Let's say if nothing happened, then
Your evaluation would be based on your test materials. But given that we have the pre-lab material as well. So you need to have that one as well. Okay. All right. So for the office hours, I've obtained an office, and then I'll let you know the exact time by Wednesday. And also the TAs, we have assigned the TAs, but for specific hours, just check again on Wednesday. I'll update the website as well. And also I'll update these slides, and I'll put it back as a revised version on the wiki page as well. So again, just make sure if you're in the Lab 01, attend it on the Mondays at 7. If you're in Lab 02, attend it only on Tuesdays. So that was a reference. We started to have a look. This will change. So we reached up to the point that we were talking about opening the box inside a computer and see how we're going to speed up the processes, the task, and the instructions running on the computer. And we were trying to understand and set stone about some different methods to understand performance in algorithmic level, in a programming language or compilation level, in processor level, and in input and output or operating system level, right? So we reached up to the point that we were talking about how a high-level language is going to compile to generate an assembly using a compiler, an assembler, and how does the assembler after that is going to generate machine-read, binary code, and then we actually run that on our hardware, right? So we are trying to familiarize with this process in this course. We were talking about a big picture of components of a computer as an input-output control data path, and then we carried on with the high-level view of starting from transistors, and then how they derive from a silicon ingot up to a chip that yields performance for your computer. So, all right. So this session we're gonna carry on this introductory conversation, and we hope we can finish the first chapter today. And on Wednesday we're gonna start the first chapter, which is the beginning of instruction set architecture of RISC-V, and you're gonna learn gradually how does the assembly work in RISC-V actually. All right. So if you recall that video that I showed at the end of the previous lecture, so from the sand we extracted the silicon and we made an alloy with that, and then we slice it and whatnot. So we are up to the point that we reached to a wafer. So that specific wafer is for Intel i7 core with this 32 nanometer technology, right? So the companies that fabricate and produce this wafer needs to have some formulas in order to understand what's going to be the output of their product. So let's have a look at 3 simple formulas regarding that. All right, the first one is pretty straightforward. So the cost per die is actually your cost per wafer divided by dies per wafer, and the yield, which is the amount of dies inside that wafer that they're actually functional on, right? Coming back to that figure again, so starting from the silicon ingot, they made an alloy, they slice it, they design the blank wafers, and they repeat this process several times, and they make a pattern out of that. So when it comes to test that pattern, some of them might fail. Some of the transistors might fail, right? So they need to repeat the process with a dicer and then test the dies again. So this process, we can define a yield metric that understands the proportion of working dies per wafer. Say if one of them doesn't yield anything, so you're out of 6, your 5 out of 6 yields the performance. You need a chair? Yeah, come pick up. There's another one here as well. You can take this. Well, actually, there's another one here. Yeah. So everyone is seated almost, yeah. Yeah. All right. So having the yield metric, we can compute the cost per die, right? It's going to be cost per wafer divided by cost per wafer, multiply the yield of that dies per wafer. So the second formula approximates almost the dies per wafer is approximately equal to wafer area divided by die area. Does anyone know why this is an approximation and it's not an equal sign? Because it makes sense it should be equal.
Wafer is circular.
What is it?
Is it because the wafer is circular?
Right. Yeah, because our wafer are circular, right? So what happens in the corners? In the corners we miss almost a little bit of our area. So that's why it's almost as an approximation for that. And the third one is coming actually from the empirical results of companies when they produce the chips. So it's actually an empirical data at integrated circuit factories, and that the exponent related to the number of critical processing step, right? And as you see, it's not linear. So we have an exponent over there. So now at least we have very preliminary formulas in order to understand how effective we've been producing dies and wafers into our integrated circuits, right? All right, now let's go back to another example. So we were talking about defining performance in the previous lecture. So now consider we have 4 different planes. Some of them are old, like BAC is, I believe it was in the 70s and 80s. It was for British, perhaps Air, and C perhaps stands for Corporation or something. Let's see. Yeah, so it was a British aircraft in the 70s. And Douglas DC also is an old one. So we have 2 different Boeings, 777 and 747. So you see, regarding different metrics, so passenger capacity, the range, the cruising range, so how far can the plane go without refueling, and cruising speed, and also the passenger mile. So you see, having different metrics, same plane, we have different outputs, right? So it just defines in what way we are looking at defining performance for our ICs and for our CPUs and for our computers, right? How fast a process can run, how big of a CPU we want, how much money we want to spend, how much processes should have been done in order to make that, right? So this small analogy leads us to define some more, interesting metrics. So first of all, if you're talking about computer architecture and organization and programs, so for us definitely response time is of importance. So what is actually response time? So it defines how long a program takes to run its task, or in a way, how long it takes to do a task on a certain computer with a program, right? So the other one that is very important is the throughput of that hardware. So the total work done per unit time, right? So we are interested in accomplishing certain amount of workload in a certain amount of time, right? So it gives us a perfect metric to understand that as well. So for instance, how many tasks, how many transactions, how many instructions were processed, input, output per hour or per certain amount of time, right? So given these two, we can define a question such as how our response time and throughput affected by other, other variables. So if we replace a processor with a faster version, say we replace our i3 with i5, still, so what are we expecting to get with a newer processor? What if we change that from i5 to i7 or i9, right? How about we add more cores? We start from a single core to a multi-core or a many-core. All right? So let's focus just for now, let's focus on the response time for now. Okay, so in a matter of performance and execution time, when we say x is n times faster than y, right? This actually means that the performance of x divided by performance of y is actually n, right? So the higher the performance, the faster it is. So you see that performance is having a negative relation with the execution time. The faster the performance is, the lower the execution time. So for instance, time taken to run a program is going to take 10 seconds on A, it's going to take 15 seconds on B, right? So the execution time of B divided by execution time of A is going to be 1.5. Thus, if we looking at this on a performance point of view, we're going to see that 1.5 A faster than B, right? Is it clear? All right. So now that we know the relation between performance and execution time, let's talk about some other more detailed measurements for execution time. So we have elapsed time, which accounts for total response time, including all aspects, from the point that you input, the point that it was processed in the OS, all the overheads of the OS, and then the idle time if the OS was putting the program into wait or halt or some cycles of pause, and then up to the point that you receive the output, right? So it's going to be the elapsed time. There is another one inside elapsed time that accounts only for the CPU time, right? So some portion of that elapsed time might account for the CPU. So and that's exactly referring to time spent processing the job only, right? And as you can imagine, it discounts the input-output time and other non-processing factors from that elapsed time. All right? So let's focus on the CPU time for now. So this figure shows that depending on the clock of your CPU, when you say you have a CPU of 4 gigahertz, 2 gigahertz, or in the past it was in a matter of megahertz. So it shows how fast the clock cycle of the CPU works, right? So the faster the clock cycle, the smaller these fluctuations, right? 0 and 1s. So each time it goes 0 and 1, so we're going to call it one clock period, right? The faster the clock is, the smaller are your clock period, so faster they can have cycles. So, as an example, when you have a clock period of 250 petasecond, it's as if you have 0.25 nanosecond or 250 multiply, I'm sorry, it was pico, not peta, because it's minus, it's 250 multiply 10 to the minus 12 seconds, right? So now if you want to calculate the clock frequency or the rate of the clock, so actually 4 gigahertz, now you know that it stands for, because giga is 9, 10 to the raise of 9, so you actually understand that at each second you have 10 to the raise of 9 times clock period for your CPU, right? So given this small introduction, we can define CPU time as a form of clock cycles and number of clocks it takes for for a certain task to complete its CPU time, right? So CPU time stands for CPU clock cycle, some hertz, multiply clock cycle time, each of those. Or you can define it as CPU clock cycles divided by the rate of the clock, right? So the higher the rate, the smaller the CPU time. If you change your CPU from, I don't know, 1.5 to 2, you're expecting to have some performance increase. By how much? We're gonna have an example shortly. And let's see if we change our CPU. Say we bought a new CPU, and the chip chip speed is from, I don't know. In the past we had 2 gigahertz. Now it's 4 gigahertz, right? Are we expecting a 2x speed up or not? Let's see how does the relation between the clock rate and the overall CPU time goes in computer architecture. Any questions so far? Right. All right. So example, we had a computer. It used to work at 2 gigahertz. So a task or a program was taking 10 seconds, right? So his CPU time was 10 seconds. Now, we've got a designer. He wants to design a new computer, a new chip for us, right? And he's trying to aim for 6 seconds as the new CPU time for the new task. So we are interested in having our task finished by the 6th second instead of the 10th, right? So he's trying to design the new chip, and he's coming up back to you and says, okay, I can do the faster clock, but this causes 1.2 multiply the clock cycles for the rest of the CPU design, right? I need to increase that by that amount in order to include certain more functionalities in order to do that job in 6 seconds. So now, let's see the clock rate of the new computer now. So the clock rate, as I taught in the previous slide, is going to be the clock cycles of the computer B, the new computer, divided by the CPU time of the new computer. We were aiming at 6 seconds. The new clock cycle is 1.2 of the previous one, right? And then, by the time we calculate the clock rate of the new computer, we see that in order to offset this time and make it faster from 10 seconds to 6 seconds, given the other constraints, now we need to have a processor that works at 4 gigahertz. So we are doubling the processors, but we are not halving the CPU time in this case. So you see that it's not that easy just to double the amount of CPU, double the speed of the CPU, double the clock speed of the CPU, and then expect everything is going to go double speed now, right? There are other constraints involved, and we're going to learn more and more about that in this course. Is it intuitive? Okay. Now let's add one more level of detail on this performance evaluation. So we talked about the task. Let's zoom into tasks and define what tasks are actually meaning. So how do we define tasks? Are they lines? Are they, I don't know, cycles? Are there instructions? How do we define those? So one of the better metrics in order to define those is instruction count. So the number of instructions your compiler outputs from a high-level language. So you write printf hello world. So how many instructions your compiler will output that into assembly code, right? So we actually count those, and it stands for instruction count, or IC. So a better way to define clock cycles is actually by the multiplication of instruction counts and cycles per instructions. So how many instructions I have and how many cycles it takes per instructions, to process that. So you multiply these two, you have your clock cycle. Now, go back to the previous formula for the CPU time. Now we can, just add this into its position, and then we're gonna have CPU time is equal to instruction count, CPI, which is instruction cycle per instruction. So cycle per instruction, CPI, multiply clock cycle time, and then actually it is equal to instruction count multiply clock per instruction, total amount of work, and then divided by the clock rate. The faster the clock rate, the lower the final value would be, which is the which is the CPU time, right? So if you increase your clock rate, your CPU time would go down. So your program would run faster, process faster. So now we have different components to play with. If you want a faster instructions count, so we need to have a better ISA, a better compiler that outputs more efficient codes, fewer number of instructions. If we and then the average cycle per instruction is actually completely determined by the architecture of the CPU, how fast it's going to process that, right? Does it use a pipelining? Does it use other optimization? Does it use forwarding or anything else? That we're going to learn later on. Question? No. Yeah. Okay. So let's see an example about this. They're pretty intuitive. I mean, you just have to learn it by feeling, I would say. You don't have to memorize anything. It just, you need to compute all the workload and the speed you want to process that workload, And that workload could be, into more fine grain and into more details. You can expand that into different layers. All right. So computer A, it has a cycle time of 250 PS. The cycles per instruction is 2, right? And computer B has a cycle time of 500 PS, and its CPI is 1.2, right? Both having the same ISA or ISA. That means that their architecture, for instance, both of them are having RISC-V ISA. They have the same 64-bit, for instance, ISA. So let's see which is faster. In order to compute that, we need to compute the CPU time for A and CPU time for B. So CPU time, as you recall from the previous slide, it was the multiplication of instruction count for the overall instruction, which we don't need it because it's gonna be both for the same, and it's gonna because we're using the same ISA and the instruction counts are the same, we don't need the number actually. So the thing that is important for us is only CPI A and a cycle time for the computer A. So I stands for that. So it's going to take 2 multiply 250, and then on the case of the B, it's going to take 1.2 multiply 500, right? So now you see that computer A is actually faster. But looking at the first one, it didn't sound like, right? And then if you divide the CPU times of B by A, you're going to see that by how much it is faster. So 600 divided by 500 is 1.2 faster, right? So that's just for a single task, a single application, or a single instruction counts. What if we have many of those, and each of those have different CPI? Question?
Sorry, I might have missed it. What's ISA?
Instruction set architecture, such as RISC-V.
Like RISC-V.
Yeah,
Okay, so.
yeah, or MIPS or ARM. Yeah. Okay, good. All right. So now let's talk about what if we have many tasks, right? and each of them has its own CPI. So if we zoom in again into that, so if you have different instruction classes, that each of them takes different number of cycles. So you'll learn in chapter 2 that normally load instructions are taking more time than save. Control instructions are taking less time than load, for instance, in general, and it depends on the architecture. You see, different instructions take different amount of cycle in CPU to process. So what if we want to have them in more fine grain, right? In this case, we have to sum them up and weight them by their own CPI, right? So each instruction count of I, it has its own CPI I. And then in order to find the overall clock cycle, we need to just sum them up from I to N and weigh them with their own CPI. And at the end, when we want to calculate the final CPI, it's going to be the weighted average CPI. Is it clear? Okay. All right, let's see an example of this. So we have two classes, right? So the CPI row, this row, is provided by the hardware designers. So as if you have two different hardwares, A, B, and C, right? It's 3 actually. And then the instruction count, the number of instructions, are output by the compiler you have. So the compiler has to emit code instructions when compiling a high-level language like C, C++, Java, or anything else, right? Now let's see by this two-dimensional data, two different hardware, different compiler, right? When we have two different sequences of IC, two different instructions, two different tasks or two different programs, which one is going to be faster, right? In each class A, B, and C. So for the sequence 1, we have instruction count equal to 5. Why is 5? Yeah. And for sequence 2, the instruction count is 6, right? And then you have to make a weighted sum here. So 2 multiply 1, 1 multiply 2, 2 multiply 3 is equal to 10. So the average CPI is that 5 is your overall 10 divided by the 5, right? On a sequence number 2, a different compiler, for instance, it would be 4 multiply 1, 1 multiply 2, and 1 multiply 3. So the answer was 9, and then it would be the average CPI is 9 divided by 6 is 1.5. Okay? You see that when we weight them, depending on the amount of cycle each task takes, we have different output now, right? Okay, so now let's put everything together in a single, I would say, more beautiful formula. So, CPU time, the overall picture. CPU time stands for instructions divided by program, multiply clock cycles divided by instructions, multiply seconds divided by clock cycle. You see, the more we go right, the more fine grain we go, right? First, starting from instructions per program, clock cycles per instructions, and then seconds plus divided by clock cycle, right? So now you see that the performance of a computer depends on many things. Algorithm, because it affects the instruction count, possibly can affect the CPI. Programming language definitely affects IC, right? Compilers for sure affects IC, depending how big of a code they're going to generate, how many instructions they're going to generate out of a single, say, print, right? And then the instruction set architecture, or the ISA, affects the basically CPI, IC, and the time as well. Okay? Does this make sense to you? I'll pause here for some seconds. Okay, so now we talked about the big picture of CPU time. So let's see how much of power is going to consume when we are targeting certain performance, right? Because power is of an important issue recently. If you're a savvy computer scientist or an engineer, you know that we are in a second power wall sort of era. And power trends are showing us that we are actually lowering the power because we can't afford to have, higher performant, chips within the same area that they take in order to perform that. If you want to make this smaller and smaller, we can't afford to just, going higher in the clock frequency. At the same time, we need to make them low power as well. Otherwise, the area becomes larger and larger. So the big picture of this definition is called power wall. And starting from the mid-2000s, they faced the first power wall. So I'll talk about it later. But for now, you just see the trend here. In the 80s, they were just going up in the clock rate, the blue line. And at the same time, the power would follow almost the same trend up to the point that Pentium 4, I'm not sure if you recall it, is from my age. When I was perhaps primary school, perhaps. Yeah, that was the best i9 we had. So, and Pentium 4 was a benchmark for speed at the time. So you see, after Pentium 4, when the clock cycle reached 3.6 gigahertz, it was pretty much very high at the time. You see that now the best CPUs are no more than 4 because they can't afford to pay the price for the power. So you see the clock rate actually went down because that was the first time they hit the power wall. Pentium 4 was a very performant architecture, very popular, but it was consuming a lot of power. And they couldn't simply afford to go higher because the power would just surpass it. 100 watts, it was a lot. You can't afford to have a personal computer that just, with a single core to spend this amount of power. So after that, you see that they try to make the process more optimized. They go low power. They define newer generations of, new family of chips. The one that are more low power are using in your cell phone devices, embedded domain, some of the laptops, and the more high performant one in the servers, and some personal computers as well. So you see that the power consumption is dropping, and they almost keep the same. Almost clock rate, right? So let's see what was the reason behind this. So roughly speaking, consumption of power is related to capacitive load of the material, the transistors, multiply voltage to the raise of 2, and multiply frequency. So in CMOS technology, so CMOS is a technology underneath your IC. It stands for complementary metal oxide semiconductor, right? So it's for they're using that technology for constructing ICs, including any ICs like microprocessors or anything else, right? So the dominant technology for ICs is CMOS actually, and for CMOS, the primary source of energy, the primary source of energy consumption for CMOS is actually coming from dynamic energy. So dynamic energy is the energy it takes a transistor to turn itself from 0 to 1 or 1 to 0, right? All we need is a material, which we found finally in transistor, that when we switch it to 0, 1 and 1 to 0, it's going to perform the task for us, because all the codes that are emitted by assembler are 0 and 1, right? We just have to mimic those 0 and 1s with a material, and that material consumes power. You have to make that process more efficient, right? That's the whole, I would say, story behind computers, right? You have all these 0 and 1s. Try to find it here. So this is the actual program that the computer runs, right? 0 and 1. So you need something that performs these switches, 0 and 1. And by each switch, it's going to consume some energy, right? And using that, you can run things on computers. So, all right. So I was talking about the major source of power for CMOS, and that is called the dynamic energy. That is the energy that is consumed when transistor switches their state from 0 to 1 and vice versa, right? And that depends on the capacitive load of that transistor with the frequency and the voltage applied. So that's the estimation. So as an example, if we want to have a power to increase by 30x, right? We need to have our frequency to increase by 1,000 times. At the same time, we need to make that voltage consumption from 5 to 1, right? This is a pretty hard task normally. And that's what it takes in every generation of computers. They want to make it more power efficient. Your laptops perhaps, I don't know, uses less than 100 watts, 70 watts, even less. Yeah, the PCs, the newer GPUs of NVIDIA, around 100 watts, 150 watts, depending on the workload. So because they can't afford to spend more power on that. Even the newer version of CPUs having multi-cores and many cores, there is another problem they call dark silicon. So let me see if I can write something here. And so say this is your 8-core. Say this is your 8-core CPU, right? Core 0, core 1, 2, 3, up to 7. So you have spent some money. That's a good CPU you got. 5, 6, right? So in most of the architectures, there is a well-known problem. I mean, which is on all the architectures, we can't afford, in most of the cases, depending on the CPU governor, we can't afford to turn them on at the same time all the time. First of all, their heat that they generate affects the performance of the adjacent cores, right? And if they are at 100% load, the power consumption would be very, very high. So the battery issues, the power issues, and so on and so forth. So the governors, you can see even in your CPU, depending on the governor on your, in your cell phone, if you install some applications to monitor your CPU governor, for instance, CPU-Z, CPU-Z, you can see that not all of your cores are on at the same time, right? So perhaps this turns off, this on, this is off, this is off, this is on, and then they try to make the adjacent one not on at the same time because they have different, impact on the adjacent, CPU cores. So this problem is known as dark silicon. And there are many researches going on, and researchers have been trying to address this. So this is just one of the issues in multi-core domain. So let's go back to our, our course, which is still in the single core up to here. So you see that by increasing the power, we need to go a long road in order to optimize that process. Is it clear? Okay. So suppose your new CPU has 85% of the capacitive load of the old CPU, and the designers managed to reduce 15% on the voltage and 15% frequency reduction, right? So the power of the new, after all these optimizations, has 0.52 of the previous generation, right? And that was the power wall I was talking about some minutes ago. So after the Moore's law, when we are at the era that actually Moore's law is no longer an issue for computer designers, because we can't afford to turn them on at first. We have hit the power wall. So optimizing the voltage, frequency, and capacitive load is of an more important issue than just increasing the clock rate, right? So you can see it actually here. So in the good old 70s and 80s, you see on average 50% increase in CPU, 80s and 90s, right? After hitting the first power wall, that increase have gone way slower to around 20%, right? And this graph only shows the uniprocessors. We're not talking about the multi-core or many cores by now. We'll touch on that later, right? So the 52% where the clock speed is in increasing, that is over now, right? As I mentioned, and it's now more architectural innovations, multi-core, many cores. So if you just think about like 30 years ago, people would just write softwares and they would just wait for a new CPU to come out. Yeah, let's wait for in 2 years our software will become faster on its own, right? But now we have to optimize it in different levels. We have to optimize the compiler. We have to optimize the way we write code, newer algorithms, new software paradigms. Are we using OpenMP, MPI? How are we going to parallelize it? And other issues. All right. That leads us to the multiprocessor era, which is the current era, right? So every chip has more than a single processor. So while this is a very good start, but this raises even more issues for us. Now, how are we going to define tasks for those? How are we going to define the constraint between the programs? Do we have dependencies in our, say, a for loop? We have a for loop. We want to do something in a for loop, some variables, assignments. And so are we having dependencies between the assignment of the variables? Are we running into issues of that? Are we going to read after a write, right? Are we going to load some variables that has been assigned in another thread at the same time, and we are losing the communication? So this yields another set of issues for itself, and perhaps you're going to learn it in, I'm not sure if you have a parallel programming course or something. Do you have something? Yeah. So that's going to be an interesting one. So for that, you need to load balance. You need to define new software paradigms, programming for performance, and optimizing the communication and synchronization between your cores to do the tasks, right? Okay, I have a few more slides. I'm going to just wrap it up quickly. So SPEC is an organization. You can just find them in the website. I believe it's SPEC.org. They are trying to standardize benchmarking of computers. And you have different benchmarks. So For CPU, they have one of the latest one is SPEC CPU 2006. They have benchmarks for integer variables and for floating point variables as well. So the way they do is trying to normalize away different tasks or different programs, different standard programs as benchmarks are running within a certain architecture. And they report the number by averaging them. But as you know, when you have speed ups, you can't just simply average them by arithmetic mean. You can't multiply them and divide it by the number. The correct way to average a speed up is by geometric mean. So that's the formula for a geometric mean. If you use, I don't know, MATLAB, Python, or Excel, or whatever, so when you're calling mean, there is geo mean as well. There is harmonic mean as well. So they have another application. So, but in general, as a rule of thumb, when you have a speed up numbers, 1.2, 1.7, whatever, when you want to try to compare different speed up, depending on from which angle you look at the speed up, so say you have two computers, right? If you base your speed up on the first computer or the second computer, when you average them, try to do the math and you see that you have different numbers. So that's why on the case of averaging speed up numbers, you need to use geometric mean, and that's the formula for that. So SPEC uses that to normalize relative to reference machine, and they have reported for the integer values, and also they have another one for the floating point values. So these are different standardized softwares, right? A video compression software, H264, a discrete event simulation, XML parsing. So these are different benchmarks that they run on each of the architectures in order to capture their performance, right? And they make an overall average, and they call that overall workload overall SSJ underscore ops. And when they add the power metric over that, so the most accurate way we have for benchmarking CPUs is overall SSJ underscore ops per watt. So how much it takes per watt, right? And then each of those comes from its own averaging. So using that, they publish periodically for each of the CPUs that comes out, i7, i9, i5, or different architectures as well for ARM. And you can just find it on the website. So this is one way to benchmark the performance, right? It's actually simplify the marketing of computers. So when you want to buy a computer, you know actually how fast is it. Because if you want to buy a computer and just ask the guy, I want a fast computer, he's going to ask, how do you define your fast, right? Do you want a low power computer? Do you want a fast CPU cycle computer? No, how do you define that fast? All right. So the last point we're going to talk about today before wrapping up the chapter 1 is the famous Amdahl's law, right? It's very intuitive. Perhaps you've already considered it sometimes when you were thinking about optimization tasks, hopefully. So when you try to have an improvement over a task, right? You always need to take into account how much of the overall workload has been improved by the new optimization scenario, right? Say you have a huge chunk of, I don't know, this bottle of water, right? If you are improving half of the water, if you found a way to, devise a new material called a new water that takes half of the weight of a water, right? And you changed half of this bottle of water with that new material that has half of the weight of a water, right? What's going to be the overall improvement you had? Simply, you have to take into account the amount of improvement per overall, material, right? And that's the premise of Amdahl's law. When you have an improvement, you need to take into account the affected area of that improvement. It doesn't affect all of your workload, right? If 10% of your workload has been doubled, it doesn't mean that your 100% has been doubled. It's that 10%. So you take the fraction of that, and then you add the t of unaffected one, the unoptimized one, right? Is that clear? All good? So that's the simplified version of Amdahl's law. They have defined many different versions of that for many core, multi-core, and different domains. So say, yeah. And as I talked before, it depends. There's another method for calculating your workload. Is that how much of performance of your CPU are you using? Are you using 100% of your CPU? Are you using 50% load of your CPU? Or are you using at 10%, right? So this is another metric that comes into play in order to compute the performance of your machine. Finally, there is a well-known metric called MIPS, and MIPS stands for millions of instructions per second. So for a long, long time, computers were, and different ISAs were benchmarked by the number of MIPS they were outputting, right? So the number of instruction counts they could execute, and the execution was for millions of instructions. So that's why you have 10 to the raise of 6 number there, right? Okay, so by now, as an introduction, we learned the cost and performance as a trade-off of improving CPU, right? We just have to take into account all the fine details of changes we do in hardware and software as well, and that's the real premise of computer architecture. And currently, power is a limiting factor, right? So we use different kind of parallelism to improve our performance. All right, any questions? No, next week. Yeah. So on Wednesday, we're going to start chapter 2, and by the end of the week, I'll post the pre-labs for you. Next week, labs next week.